Over billions of years, planet Earth has been reshaped again and again by powerful natural forces that never stopped working. Continents drifted like slow-moving giants, mountains rose from deep pressure, and entire worlds of life appeared and disappeared in silent cycles. The story of Earth is written in stone, ice, and air, capturing changes that stretch beyond human imagination. What we see today is only the latest chapter in a much larger, constantly changing planet history that began long before anything alive could witness it. The formation of the solar system and the birth of Earth began in a very distant past, when space was filled with vast clouds of gas and dust spread across large regions of the Milky Way galaxy. These clouds contained simple elements such as hydrogen and helium, along with tiny amounts of heavier elements that had been created inside earlier generations of stars. Over long periods of time, these materials slowly drifted through space, sometimes gathering into thicker regions due to gravity, and at other times spreading apart again into thinner regions. One of these thick regions became the starting point for the system that would later include the Sun, the planets, and Earth. At a certain point in this large cloud, a part of it began to collapse under its own gravity. This collapse did not happen all at once. It started in a small area and then slowly expanded outward as more material was pulled inward. As the material moved closer together, the center of the collapsing region became denser and hotter. The movement of gas and dust increased as gravity continued to pull everything inward. Over time, the center of this region became so dense that it formed a growing mass of material that would later become the Sun. As this central mass continued to gather more material, it also began to spin. The spinning motion came from the small natural movements already present in the original cloud. As the cloud collapsed, the spin became faster, due to the way rotating systems behave when their material moves closer to the center. This spinning motion caused the collapsing material to spread out into a flattened shape around the growing central mass. This flattened region became a disk made of gas and dust surrounding the early Sun. The disk contained most of the material that would later form the planets, moons, asteroids, and other objects in the solar system. Inside this disk, small particles of dust began to stick together. These particles were extremely tiny at first, but they collided gently and sometimes remained attached after impact. Over long periods, these small clusters grew larger as more particles joined them. The growth was gradual and it happened throughout the disk. Different regions of the disk contained different amounts of material, and this influenced how quickly the particles could grow in each region. In the inner parts of the disk, closer to the young Sun, temperatures were very high. Only materials that could withstand strong heat remained solid in this region. These materials included metals and rocky substances. In the outer parts of the disk, temperatures were lower, allowing other materials such as water ice and different frozen compounds to remain solid. These differences in temperature influenced the kinds of objects that formed in different regions of the disk. As the small clusters of material continued to grow, they became larger bodies that could attract more material through gravity. These larger bodies are often described as early building blocks of planets. They grew as more particles collided with them and became attached. Some of these bodies became large enough to affect the motion of nearby material, clearing paths around their orbits and collecting more matter from their surroundings. Over long periods, these growing bodies collided with one another. Some collisions caused them to merge into larger objects, while other collisions broke them into smaller fragments, that later joined again in different ways. This process continued for a very long time, and it gradually reduced the number of small bodies while increasing the size of the largest ones. The largest of these bodies eventually became the planets. During this stage, the region that would become Earth was forming from a mixture of rocky and metallic materials. These materials came together under the influence of gravity, slowly building a growing sphere of hot, partially molten rock and metal. As more material fell onto this growing body, the energy from impacts added heat, causing the interior to become extremely hot. The heat also came from the decay of radioactive elements inside the material, which released energy over long periods. As the young Earth continued to grow, its interior became layered. Heavier materials such as iron and nickel began to sink toward the center due to gravity, while lighter rocky materials rose towards the outer regions. This separation of materials created a structure with a metallic core and a rocky outer region. This process occurred while Earth was still being shaped by ongoing impacts and accumulation of material from space. At the same time, the surface of the young Earth was not stable. It was constantly changing due to impacts from remaining material in the surrounding disk. Large and small objects struck the surface, adding more heat and altering the structure of the outer layers. These impacts also contributed to melting parts of the surface, which allowed materials to mix and move more easily. The early atmosphere of Earth began forming during this stage as well. Gases trapped inside the material that formed Earth were released through volcanic activity and through impacts that heated the surface. These gases rose above the surface and formed a surrounding layer of atmosphere. The composition of this early atmosphere was very different from the atmosphere present today. It contained gases such as water vapor, carbon dioxide, nitrogen, and other compounds released from the interior of the planet. Water on the early Earth also began to accumulate during this period. Some of the water came from materials that already contained ice or hydrated minerals, while other portions were released from inside the planet through volcanic processes. As the surface cooled over time, water vapor in the atmosphere began to condense and fall as liquid, slowly collecting in low areas on the surface. This led to the formation of early oceans. The surface of Earth during its early development was repeatedly reshaped by volcanic activity. Heat from the interior caused molten rock to rise toward the surface, where it cooled and solidified. This cycle of melting and cooling contributed to the gradual formation of a solid crust. The crust was not uniform and was frequently broken and reformed due to internal heat and external impacts. During this period, Earth was still being affected by large collisions with other growing bodies in space. These impacts were part of the final stages of planet formation. One of these collisions involved a large body, striking the early Earth with enough force to eject material into space. This material eventually gathered around Earth and formed a surrounding ring of debris. Over time, this debris came together to form the Moon. This event also contributed additional heat to Earth and further changed its internal structure. As the Moon formed and moved away from Earth, its gravitational influence began to affect the planet. The presence of the Moon influenced the movement of the oceans once they formed and contributed to changes in the rotation of Earth over long periods. The Earth and Moon system became linked through gravitational interaction, which continued to evolve as both bodies changed over time. The solar system continued to evolve as the remaining material in the disk was either absorbed into planets, ejected into space, or formed smaller bodies such as asteroids and comets. The inner region of the system became dominated by rocky planets, while the outer region contained large planets made mostly of gases and ice. Earth remained in the inner region where rocky material was most abundant. The surface conditions on early Earth gradually changed as the planet cooled further. The crust became more stable in some regions, allowing the first stable land areas to form. These areas were still frequently affected by volcanic activity and impacts, but over time they became more persistent. The interaction between the atmosphere, oceans, and crust created continuous cycles of material movement across the planet's surface. The energy inside Earth continued to play a major role in shaping its structure. Heat from radioactive decay and leftover energy from formation kept the interior in motion. This internal movement caused gradual shifts in the crust and influenced the arrangement of surface features. The movement of material inside the planet also contributed to the long-term cycling of elements between the surface and the interior. The early development of Earth also involved the gradual separation of different chemical components. Heavier elements moved deeper into the planet, while lighter elements remained closer to the surface. This separation influenced the long-term structure of Earth and helped define the layers that exist within it. The core remained rich in iron and nickel, while the outer regions contained silicate rocks and other lighter materials. As the planet continued to evolve, interactions between water, rock, and atmosphere became more stable. Chemical reactions occurred between these components, leading to gradual changes in the composition of the surface and the oceans. These processes were influenced by temperature, pressure, and the continuous movement of materials through volcanic activity and surface changes. The solar system's early environment still contained leftover debris from the formation process. Some of this material continued to collide with Earth and other planets, though the frequency of these impacts decreased over time. The reduction in impacts allowed the planet's surface and atmosphere to develop more stable conditions. Earth's rotation and orbit were also influenced by the early stages of solar system formation. The initial motion of the planet came from the movement of the disk from which it formed. Over time, interactions with other bodies and the Moon contributed to changes in rotation speed and axial tilt. These changes occurred gradually over long periods. The atmosphere continued to evolve as gases escaped from the interior and as chemical reactions occurred on the surface. Some gases were lost to space, while others became part of new compounds formed through interactions with sunlight and surface materials. This continuous exchange of gases shaped the long-term composition of the atmosphere. The surface of Earth eventually became more stable as the rate of large impacts decreased further. The crust thickened in some regions, and the movement of internal heat continued to reshape the surface slowly. Oceans expanded and covered large portions of the planet, interacting with the crust and atmosphere in ongoing cycles of change. Throughout this long development, the solar system maintained a structure that included a central star and multiple planets arranged in stable orbits. Earth remained one of the rocky planets formed from the inner region of the original disk. Its development was closely tied to the same processes that formed the rest of the system, including the collapse of the original cloud, the formation of the disk, and the gradual accumulation of matter into larger bodies. The long sequence of events that led to the formation of Earth began with simple particles in space and continued through many stages of growth, heating, separation, and cooling. These processes involved continuous movement of matter and energy over extremely long periods of time, shaping the planet into a layered structure with a core, mantle, crust, atmosphere, and oceans. The ongoing evolution of Earth continued as internal heat, surface processes, and external influences interacted in complex ways. The materials that formed the planet remained in motion through cycles of melting, solidification, erosion, and deposition. These processes were linked to the planet's internal energy, and the conditions established
early Earth and the formation of the first crust. Early Earth existed during a distant period of planetary history, when the planet was still developing its fundamental structure. At that time, there were no oceans, forests, continents, animals, or any of the familiar environments that characterize the modern world. The surface was dominated by intense heat, widespread volcanic activity, and constant geological change. Earth was a young planet whose interior and exterior were being shaped by powerful natural processes that operated on a global scale. The formation of the first crust was one of the most important developments during this era, because it marked the beginning of a solid outer layer that would eventually support all later geological and environmental evolution. Earth formed approximately 4,540 million years ago from material that surrounded the young sun. This material consisted of enormous quantities of dust, rock fragments, metallic particles, and other substances that occupied a rotating disk around the center of the solar system. Through the influence of gravity, small particles gradually combined into larger bodies. These larger bodies continued to collide and merge with one another, creating increasingly massive objects. Over long periods of time, one of these growing planetary bodies became Earth. The process of planetary growth generated extraordinary amounts of heat. Every condition transferred energy into the developing planet. Some impacts involved relatively small objects, while others involved bodies many kilometers across. As these objects struck Earth, their motion was converted into thermal energy. The continual accumulation of material caused temperatures throughout the young planet to rise to extremely high levels. Gravity also contributed significantly to the heating of Earth. As the planet became larger, its growing mass compressed material toward the interior. This compression increased pressure deep within the planet and generated additional heat. At the same time, radioactive elements trapped within Earth's rocks released energy through radioactive decay. The combined effects of impacts, compression, and radioactive heating created conditions that caused extensive melting throughout much of the young planet. As temperatures continued to rise, large portions of Earth entered a molten state. Vast quantities of rock melted, producing an environment in which liquid material dominated the outer regions of the planet. Scientists often describe this stage as a magma ocean because extensive areas of molten rock may have covered much of the surface. Instead of solid ground, glowing liquid rock occupied enormous regions of the planet. Temperatures were high enough to keep many materials in a molten condition for extended periods. The existence of widespread molten material allowed Earth to undergo a process known as differentiation. When a planetary body becomes molten, materials with different densities can separate naturally. Dense substances move downward under the influence of gravity, while lighter substances tend to move upward. This process transformed Earth from a relatively mixed collection of materials into a planet with distinct internal layers. Iron and nickel were among the densest materials present within the young Earth. As melting became widespread, these metals gradually migrated toward the center of the planet. Over time, they accumulated to form the core. The movement of such enormous quantities of metal released additional heat, contributing further to Earth's internal energy. Surrounding the core, less dense rocky material formed the mantle. Above the mantle, the lightest materials became concentrated closer to the surface and eventually contributed to the development of the first crust. The formation of the first crust began when parts of the molten outer layer started to cool. heat continuously escaped from Earth into space. Although the planet remained extremely hot overall, the outermost regions gradually lost enough energy for minerals to crystallize from molten rock. Small crystals formed as temperatures decreased. These crystals joined together to create solid rock. Through this process, the earliest crustal material appeared on the surface of Earth. The first crust was probably thin and unstable. Conditions on the young planet were far more extreme than those seen today. Large quantities of heat still flowed outward from the interior, and volcanic activity remained widespread. Newly formed crust may have been repeatedly broken, melted, buried, and reformed. Rather than existing as a permanent and continuous shell, the earliest crust likely appeared and disappeared in different regions as geological activity continued. Scientists believe that much of this early crust was basaltic in composition. Basalt is a dark volcanic rock that forms when magma rich in iron and magnesium cools and solidifies. Because the mantle contained abundant iron and magnesium, basaltic magma was common during Earth's early history. As this magma reached the surface and cooled, extensive basaltic crust developed. The earliest solid surface may therefore have consisted largely of dark volcanic rock covering broad regions of the planet. Even after crust formation began, Earth remained exposed to frequent impacts from space. The solar system was still relatively young and contained numerous leftover objects from planetary formation. Asteroids, planetesimals, and other rocky bodies regularly crossed Earth's path. Many eventually collided with the planet. These impacts varied greatly in size and energy. Smaller impacts produced localized damage, while larger collisions had global consequences. Some impacts released enough energy to melt extensive portions of existing crust. Newly formed rock could be shattered, buried beneath debris, or returned to a molten state. As a result, the earliest crust experienced continual destruction and renewal. Regions that cooled and solidified could later be erased by powerful impacts and replaced by new crust formed from cooling magma. One of the most significant events in Earth's earliest history involved a collision with a large planetary body, Mars. According to the leading scientific explanation, the fall struck the young Earth during the planet's formative stages. The impact released an extraordinary amount of energy and dramatically altered Earth's outer layers. Large quantities of material were injected into space, and some of this material later combined to form the giant impact had profound effects on the developing crust. Any crust that existed before the collision was likely destroyed or severely disrupted. Much of Earth's outer region may have melted again, creating conditions similar to those that existed during the earlier stages of planetary formation. Following the impact, Earth entered another prolonged period of cooling, during which fresh crust gradually formed from newly solidifying magma. Because of the intense geological activity that characterized this period, direct evidence from the earliest crust is extremely rare. Most ancient rocks have been altered, recycled, or destroyed through billions of years of tectonic activity, volcanic processes, and erosion. Nevertheless, small mineral crystals known as zircons provide valuable clues about conditions on young Earth. Some zircons discovered in ancient rocks are more than 4 billion years old, and preserve information about temperatures, water, and crustal processes that existed during Earth's earliest history. These ancient zircons suggest that crust formation may have begun relatively soon after Earth formation. Their chemical characteristics indicate that liquid water may have been present surprisingly early in planetary history. If water existed at the surface during this period, interactions between water and crustal rocks could have influenced the development of the earliest geological environments. As crust formation continued, volcanic activity remained a dominant force. Large quantities of magma rose from the mantle and erupted onto the surface. Volcanic eruptions released gases that had accumulated within Earth's interior. Water vapor, carbon dioxide, nitrogen, sulfur compounds and other gases entered the atmosphere through these eruptions. Over time, volcanic outgassing played a major role in creating the planet's earliest atmosphere. The atmosphere that existed during crust formation differed greatly from the atmosphere of the modern Earth. The oxygen was either absent or present only in extremely small amounts. Instead, volcanic gases dominated atmospheric composition. Thick clouds of water vapor may have covered much of the planet, while carbon dioxide and other gases contributed to atmospheric pressure and temperature. As Earth gradually cooled, water vapor in the atmosphere eventually condensed into liquid water. This process may have led to the formation of some of the earliest bodies of water on the planet. Rainfall could have occurred repeatedly over long periods. Water collected in low-lying regions and interacted with newly formed crustal rocks. These interactions contributed to chemical weathering and the redistribution of minerals across the surface. The presence of water may have influenced crust formation in several important ways. Water can lower the melting temperature of rocks and affect the movement of magma within the crust and mantle. It also promotes chemical reactions that alter minerals and create new geological materials. As water became increasingly abundant, the processes shaping Earth's crust became more diverse and complex. The first crust was not necessarily identical to the modern oceanic or continental crust. Scientists continue to investigate the nature of these earliest rocks. Some evidence suggests that the initial crust may have consisted mainly of basaltic material, generated directly from mantle erosion. Over time, repeated cycles of melting, crystallization, and chemical alteration may have produced more evolved crustal compositions. Internal heat remained one of the most important, potent factors controlling crustal evolution. The young Earth contained much more heat than it does today. Large amounts of radioactive material were still present, and heat left over from planetary formation continued to flow outward. This intense internal energy drove vigorous mantle movement beneath the crust. Such movement influenced volcanic activity, crustal recycling, and the creation of new geological structures. Many scientists believe that processes related to plate tectonics may have begun during the early stages of Earth's history, although the exact timing remains uncertain. Modern plate tectonics involves the movement of large sections of crust across the surface of the planet. During the earliest periods, crustal movement may have operated differently because temperatures were higher and geological conditions were more extreme. Nevertheless, some form of crustal recycling may already have been occurring. The continual formation and destruction of crust helped shape Earth's developing surface. New magma emerged from the mantle and solidified into fresh rock. Older crust was broken apart, buried, melted or altered by geological activity. These cycles gradually changed the composition and structure of the planet's outer layer. Chemical differentiation within the crust also became increasingly important. As magma cooled, different minerals crystallized at different temperatures. This process separated chemical elements into distinct mineral groups and contributed to the growing diversity of crustal rocks. Over time, repeated episodes of melting and crystallization produced increasingly complex geological materials. The earliest crust formed under conditions of extraordinary heat, intense volcanism, frequent impacts, rapid geological change, and powerful internal activity. Every region of the planet was influenced by processes occurring both at the surface and deep within the interior. Cooling magma, crystallizing minerals, mantle circulation, atmospheric development, impact events, and volcanic eruptions all played essential roles in shaping the first solid outer layer of Earth. The formation, modification, destruction, and renewal of this primitive crust continued throughout the earliest chapters of planetary history as the young Earth gradually developed the geological foundation upon which new later environments would emerge. About 4.5 billion years ago, the young Earth existed in a very different form from the planet known today. The solar system itself was still developing from the enormous cloud of gas and dust that had collapsed under gravity. Around the young sun, countless fragments of rock, metal, and ice moved through space in crowded and unstable paths. These materials gradually joined together through repeated collisions, forming larger bodies known as planetesimals. Over time, many of these planetesimals merged into protoplanets, which were the early versions of the planets that now orbit the Sun. During this period, Earth was not yet a stable world with oceans, continents, and an atmosphere suitable for life. Instead, it was a growing planetary body that continued to gather material from its surroundings. Every collision added mass and energy. Many impacts released enormous amounts of heat, causing large portions of the young planet to melt. Earth was therefore a hot and dynamic world, undergoing constant change. One of the most significant events in the entire history of Earth occurred during this early stage. This event eventually led to the formation of the Moon. Modern scientific evidence indicates that the Moon was not simply captured by Earth's gravity after falling elsewhere, nor did it separate directly from Earth through a gradual process. Instead, the leading explanation is that a massive collision occurred between the young Earth and another planetary body. This event is commonly known as the Giant Impact. The object that struck Earth is often referred to as Theia. Scientists use this name for the hypothetical protoplanet believed to have participated in the collision. Theia was likely a large object that formed in a similar region of the solar system as Earth. It probably contained rock and metal, and may have possessed a composition similar to that of Earth itself. Theia was not a small asteroid or a minor fragment of debris. Current models suggest that it may have been approximately the size of Mars. Such an object would have contained a tremendous amount of mass. As planets and protoplanets moved around the Sun during the chaotic early stages of solar system development, their paths could change because of gravitational interactions. These interactions may have slowly altered Theia's orbit until it eventually crossed Earth's path. For a period of time, Earth and Theia likely travelled around the Sun on separate orbits. The gravitational pull of nearby planets and other large bodies may have gradually changed these orbits. Small changes accumulated over long periods. Eventually, Earth and Theia found themselves moving toward a future collision. The exact details of the approach remain uncertain, because no direct observations exist. Scientists reconstruct the event using computer simulations, studies of lunar rocks, investigations of Earth's composition, and knowledge of planetary formation. These lines of evidence help researchers understand what likely happened during this ancient event. When Theia approached Earth, both bodies were moving at extremely high speeds. Planetary collisions involve energies far beyond anything experienced in human history. The impact was not a gentle encounter. It released an enormous amount of energy within a short period of time. The collision transformed both worlds. Many scientific models suggest that the impact occurred when Earth was already largely differentiated. This means that the heavier materials inside Earth had begun sinking toward the center, forming a metallic core, while lighter rocky materials remained closer to the surface. Earth may already have possessed a distinct internal structure at the time of the collision. As Theia struck Earth, vast quantities of material were ejected into space. Rock from Earth's outer layers and material from Theia were blasted away from the immediate impact region. Temperatures rose dramatically. Large portions of both bodies melted or vaporized. The collision generated conditions so extreme that solid rock behaved in ways that are difficult to imagine under ordinary circumstances. The impact likely altered Earth's rotation. Before the collision, Earth may have rotated at a different rate and possessed a different orientation in space. The enormous transfer of energy and momentum associated with the impact changed these properties. The present Earth-Moon system may therefore owe many of its characteristics to this single event. The immediate aftermath of the collision was chaotic. A large amount of debris surrounded Earth. Some material escaped into space completely. Some fell back onto Earth. A significant portion entered orbit around the planet. This orbiting material consisted of molten rock, vaporized rock, and fragmented debris. The region around Earth following the impact may have resembled a vast disk of material encircling the planet. Within this disk, countless particles moved under the influence of gravity. Collisions occurred continuously among the fragments. Some particles merged into larger bodies. Others broke apart again. Over time, gravity encouraged material to gather into increasingly larger concentrations. As these concentrations grew, they began forming a single dominant body. This body eventually became the Moon. Rather than appearing instantly, the Moon developed through a process of accumulation. Smaller fragments joined together repeatedly. Gravity helped draw material inward. Through many collisions and mergers, the growing lunar body increased in size. The timescale of lunar formation remains an active area of research. Some models suggest that much of the Moon may have formed relatively quickly after the impact. Other studies propose more complex processes occurring over longer periods. Regardless of the exact timing, the Moon emerged from the debris generated by the giant collision. One important piece of evidence supporting this explanation comes from the composition of lunar rocks. Samples collected during the missions of the Apollo program revealed that many lunar materials closely resemble rocks from Earth's outer layers. Scientists studying oxygen isotopes and other chemical signatures found striking similarities between Earth and Moon materials. These similarities present challenges for older theories of lunar origin. If the Moon had formed somewhere entirely different from the solar system and was later captured by Earth's gravity, scientists would expect more substantial compositional differences. Instead, the Moon appears to share a close relationship with Earth, consistent with a common origin involving the giant impact. The Moon also contains a relatively small iron core compared with Earth. This observation fits the giant impact model. If much of the Moon formed from material originating in the outer layers of Earth and Theia, the resulting body would naturally contain less metallic core material than Earth itself. The Moon's internal structure therefore provides another clue regarding its formation. The collision had profound consequences for Earth. Enormous amounts of heat generated by the impact likely melted large portions of the planet. Some researchers suggest that Earth may have possessed a global magma ocean after the event. In such a state, extensive regions of the surface would have consisted of molten rock rather than solid crust. As Earth gradually cooled, heavier materials continued moving toward the center, while lighter materials rose upward. These processes contributed to the further development of Earth's internal structure. crust, mantle, and core became more clearly defined as cooling progressed. The newly formed moon also experienced intense heat during its early history. Evidence suggests that much of the young moon was molten. Scientists believe a lunar magma ocean may have covered substantial portions of its surface. Over time, this molten material cooled and solidified, producing the rocks that make up the lunar crust. The giant impact influenced Earth's rotation in lasting ways. The modern length of Earth's day is connected to interactions between Earth and the Moon. Shortly after the Moon formed, it likely orbited much closer to Earth than it does today. At that time, the Moon would have appeared far larger in the sky. Gravitational interactions between Earth and the Moon created tidal forces. These forces affected both bodies. Over billions of years, tidal interactions gradually slowed Earth's rotation. As a result, days became longer. At the same time, energy transferred through these interactions caused the Moon to slowly move farther away from Earth. Measurements made using laser reflectors placed on the lunar surface show that the Moon continues to drift away from Earth even today. This movement occurs very slowly, but over vast spans of time it becomes significant. The present distance between Earth and the Moon therefore differs substantially from the distance that existed shortly after lunar formation. The Moon's presence has had important effects on Earth's long-term evolution. Its gravitational influence contributes to tides in Earth's oceans. These tides affect coastlines, ocean circulation, and many natural processes. The Moon also influences the stability of Earth's axial tilt. Earth's axis is not perfectly upright relative to its orbit around the Sun. Instead, it is tilted. This tilt produces the seasons experienced across the planet. Studies suggest that the Moon helps stabilize this tilt over long periods. Without such stabilization, Earth's orientation might experience larger variations. The giant impact therefore influenced not only the formation of the Moon itself, but also many aspects of Earth's later development. Features of the Earth-Moon system observed today can often be traced back to the consequences of that ancient collision. Scientists continue refining their understanding of the event. Advances in computing allow increasingly sophisticated simulations of planetary impacts. These simulations explore different impact angles, speeds, sizes, and compositions. Researchers compare simulation results with observations of Earth and the Moon to determine which scenarios best match reality. Some models suggest that the impact may have occurred at a relatively shallow angle. Others investigate more direct collisions. Different impact conditions produce different distributions of debris and different final outcomes. Scientists examine these possibilities carefully because even small changes in collision parameters can significantly affect the resulting Earth-Moon system. The role of Thayer's composition also remains an important topic of study. If Thayer formed in a region close to Earth, it may have possessed chemical characteristics very similar to those of Earth. This possibility helps explain why lunar rocks resemble terrestrial rocks so closely. Other models investigate mechanisms that could have mixed material thoroughly during the impact itself. The giant impact hypothesis has evolved considerably since it was first proposed. Early versions explained many observations but left unanswered questions. As new evidence emerged, scientists modified and improved the models. The modern understanding of lunar formation incorporates decades of research, from astronomy, planetary science, geology, geochemistry, and computer modeling. Meteorites provide additional clues about conditions during the early solar system. Many meteorites preserve ancient materials dating back to the earliest stages of planetary formation. By studying these objects, scientists gain insights into the environment in which Earth and Theia formed. Such information helps researchers construct more accurate models of the giant impact. The study of other planetary systems has also contributed to understanding. Observations of young stars reveal disks of gas and dust where planets are forming. Astronomers have detected evidence of collisions among planetary bodies around distant stars. These observations suggest that giant impacts may be a common feature of planetary evolution throughout the universe. Within our own solar system, evidence exists that major collisions affected other worlds as well. Large impact basins, unusual rotational properties, and distinctive planetary characteristics often point toward violent events during planetary formation. The Earth-Moon system appears to represent one particularly dramatic example of such processes. The energy involved in the collision that formed the Moon was extraordinary. The kinetic energy carried by a Mars-sized object moving through space at planetary velocities was sufficient to melt vast quantities of rock. Temperatures reached levels at which materials behaved very differently from their ordinary states. Rock could melt, vaporize, and mix extensively under these conditions. Following the impact, the debris disks surrounding Earth underwent continual change. Gravity sorted material according to its orbital motion. Collisions among particles converted some energy into heat. Larger clumps attracted additional matter. Over time, the chaotic cloud evolved into a more organized system dominated by the growing Moon. As the Moon accumulated mass, its own gravity increased. Stronger gravity allowed it to attract additional debris more effectively. The growing lunar body eventually cleared much of the surrounding material from its orbital region. Some remaining debris may have fallen onto Earth or the Moon, contributing additional material to both worlds. The surface of the young Moon was very different from the familiar landscape visible today. Extensive melting likely covered large regions. As cooling proceeded, minerals crystallized from molten rock. Different minerals formed at different stages, depending on temperature and composition. These processes produced layers within the lunar crust and interior. The ice that emerged after the impact also continued changing for hundreds of millions of years. Cooling allowed crustal materials to solidify. Volcanic activity remained widespread. Gases released from Earth's interior contributed to the development of the atmosphere. Water accumulated on the surface through processes that scientists continue to investigate. The giant impact occurred long before the appearance of life. Nevertheless, it helped establish conditions that would later characterize Earth. The existence of the Moon, the length of Earth's day, the behavior of tides, and aspects of Earth's rotational stability all bear the influence of this ancient event. Modern laboratory studies contribute valuable information to lunar formation research. Scientists analyze isotopes, minerals, and chemical elements contained within lunar samples and terrestrial rocks. Precise measurements reveal subtle patterns that help reconstruct events from billions of years ago. These investigations continue to improve understanding of how the Moon formed. Space missions have also played an important role. Samples returned from the Moon provide direct evidence unavailable through telescopic observation alone. Orbital spacecraft have mapped the lunar surface, measured gravitational variations, examined mineral distributions, and studied the Moon's internal structure. Each new dataset contributes additional pieces to the larger picture. Researchers continue exploring unresolved questions. They investigate exactly how much material originated from Earth and how much came from Theia. They study the timing of lunar formation, the thermal evolution of both bodies, and the detailed dynamics of the impact itself. new theories and refinements emerge as evidence accumulates. The collision that formed the Moon stands as one of the defining events in Earth's earliest history. It occurred during a period when the solar system was still young, and planetary bodies frequently interacted through powerful collisions. The encounter between Earth and Theia reshaped both worlds, generated a vast cloud of debris, and ultimately produced the natural satellite that continues to orbit Earth today. Through the combined efforts of geology, astronomy, physics, and planetary science, researchers continue uncovering details about this remarkable event and the processes that transformed a violent collision into the Earth-Moon system observed across the present age. The Hardian Eon was the earliest chapter in Earth's history. It began about 4,540,000,000 years ago, shortly after Earth formed from the cloud of gas and dust that surrounded the young Sun. This period lasted until about 4 billion years ago. During this immense stretch of time, Earth was very different from the world that exists today. There were no oceans filled with life, no continents covered by forests, no animals, no plants, and no breathable atmosphere. The planet was a young world still in the process of taking shape. It was a place of intense heat, widespread volcanic activity, constant impacts from space, and powerful geological changes that affected every part of its surface and interior. When Earth first formed, it was created through the gradual accumulation of countless pieces of rock, dust, and other material orbiting the young Sun. These particles repeatedly collided and stuck together. Over time, larger and larger bodies formed. The growing Earth attracted more material because of its increasing gravity. Each collision released enormous amounts of energy. The kinetic energy of incoming objects was transformed into heat upon impact. As a result, the young planet became extremely hot. The early Earth did not begin as a solid and stable world. Instead, much of the planet existed in a molten state. Vast regions of the surface were covered by oceans of liquid rock, known as magma. Temperatures were high enough to melt many minerals and prevent the formation of a long-lasting solid crust. The entire planet experienced conditions that would be difficult to imagine today. Large areas glowed from the heat of the molten material, and volcanic activity occurred on a scale far greater than anything observed in the modern world. Several factors contributed to this extreme heat. One major source was the energy released during the formation of the planet itself. Every impact added heat to Earth's growing mass. Another source came from gravitational compression. As Earth accumulated more material, its increasing weight caused the interior to become compressed. This compression generated additional heat deep inside the planet. Radioactive elements also played an important role. Certain unstable atoms naturally release energy as they decayed. On early Earth, radioactive elements were more abundant and produced substantial amounts of heat. Together, these processes kept the young planet extremely hot for millions of years. As the interior remained molten, Earth underwent a process known as planetary differentiation. In this process, materials separated according to their density. Heavier substances, such as iron and nickel, gradually sank toward the center of the planet. Lighter materials moved upwards towards the outer regions. This sorting process transformed Earth from a relatively mixed collection of material into a layered planet with distinct internal structures. The sinking of dense metals toward the center released even more heat. Huge amounts of gravitational energy were converted into thermal energy as heavy material moved inward. Eventually, a metallic core formed deep inside the planet. Around the core developed a thick mantle composed mainly of hot, silicious rocks. Above of the mantle, the earliest crust began to appear. This layered structure remains a fundamental feature of Earth today, although the early version was much hotter and far less stable. One of the most dramatic events during the Hadean Eon likely occurred very early in Earth's history. Scientists believe that a large planetary body, often called Theia, collided with the young Earth. This impact was among the most significant events in the formation of the Earth-Moon system. The collision released extraordinary amounts of energy. Large quantities of rock and debris were thrown into space. Some of this material eventually gathered together and formed the Moon. The aftermath of this collision probably left much of Earth's outer layers molten once again. Temperatures rose dramatically and extensive magma oceans may have covered large portions of the planet. The impact altered Earth's development in many ways. It influenced the formation of the Moon, affected Earth's rotation, and may have contributed to the structure of the planet's interior. Following this giant collision, Earth remained an active and violent world. The surface was continuously reshaped by volcanic eruptions, impacts from space, and movements within the molten interior. The crust that occasionally formed was often unstable. Regions of solid rock could melt again due to rising heat from below or be destroyed by large impacts from above. The atmosphere of the Hadean Earth was very different from the modern atmosphere. Today, Earth's atmosphere contains abundant oxygen and supports a wide variety of living organisms. During the Hadean Eon, oxygen was either absent or present only in tiny amounts. The early atmosphere likely consisted of gases, released from the planet's interior through volcanic activity. Volcanoes released enormous quantities of water vapor, carbon dioxide, nitrogen, sulfur compounds, methane, and other gases. These gases accumulated above the planet and formed a primitive atmosphere. The exact composition changed over time as volcanic activity continued and chemical reactions occurred within the atmosphere and on the surface. Volcanic outgassing was one of the most important processes during this period. As molten rock rose toward the surface, dissolved gases escaped into the atmosphere. Countless volcanic eruptions occurred across the young planet. These eruptions released material into the air and reshaped large areas of the surface. Volcanic landscapes dominated much of the Hadean world. The atmosphere provided some insulation by trapping heat. At the same time, it was subjected to intense radiation from the young sun. Conditions differed greatly from those experienced on modern Earth. Chemical reactions driven by sunlight, heat, and volcanic gases continually altered the atmospheric composition. One of the most significant developments during the Hadean Eon was the gradual appearance of liquid water. Water vapor released through volcanic activity accumulated in the atmosphere. As Earth slowly cooled, temperatures eventually fell enough for some of this vapor to condense into liquid water. Clouds formed in the atmosphere and rain began to fall. The rainfall may have continued for extremely long periods. Water collected in low-lying regions and gradually formed the earliest oceans. These first oceans represented a major change in Earth's history. The presence of liquid water created new environments and influenced geological and chemical processes across the planet. The exact timing of ocean formation remains an area of scientific investigation. Evidence from ancient minerals known as zircons suggests that liquid water may have existed surprisingly early in Earth's history. Some zircons appear to have formed in the presence of water more than 4 billion years ago. These tiny crystals provide valuable clues about conditions during the Hadean Eon, because very little rock from that period has survived. The formation of oceans did not immediately create a calm environment. The Hadean Earth remained highly active. volcanic eruptions continued, and impacts from space still occurred frequently. Large asteroids and comets regularly struck the planet. Some impacts were powerful enough to vaporize water, melt rock, and alter large regions of the surface. The early solar system contained many leftover objects from planetary formation. These objects followed unstable orbits and frequently collided with planets and moons. Earth experienced countless impacts during the Hadean eon. Many craters formed, although most evidence of them has been erased by later geological activity. Among the most intense periods of bombardment may have been an event known as the Late Heavy Bombardment. Some scientists propose that this occurred around 4,100,000,000 to 3,800,000,000 years ago. During this interval, impacts may have increased significantly as large numbers of asteroids and other objects struck the inner planets. The exact details remain debated, but there is substantial evidence that impacts played an important role in shaping Earth's own environment. Each major impact released tremendous amounts of energy. Rock-formative shockwaves traveled through the crust, and large quantities of material were ejected into the atmosphere. Some impacts may have temporarily altered climate conditions. Others could have affected the chemistry of oceans and the atmosphere. The crust of the Hadean Earth differed greatly from modern continental crust. The earliest crust was probably thin, unstable, and frequently recycled back into the interior. Rising magma continually created new rock, while other regions melted or sank. This constant renewal meant that very little of the original crust survived into later eras. Scientists have searched extensively for direct evidence from the Hadean eon. However, finding such evidence is extremely difficult because most rocks from that period have been destroyed. Earth's active geology continuously recycles crust through processes such as erosion, metamorphism, melting, and tectonic activity. As a result, rocks older than 4 billion years are extremely rare. Some of the most important evidence comes from zircon crystals discovered in ancient rocks, particularly in regions of present-day Australia. These zircons formed during the Hadean eon and have survived despite the destruction of the rocks in which they originally formed. Their chemical composition provides valuable information about early Earth conditions. Studies of zircons suggest that portions of Earth's surface may have cooled enough to support liquid water relatively early. Some evidence also indicates that crustal recycling and other geological processes were already occurring. These findings have changed scientific understanding of the Hadean world. Earlier views often described the entire planet as completely molten for extended periods, but more evidence suggests a more complex picture involving both hot conditions and localized regions of cooler crust. Heat flow from Earth's interior was much greater during the Hadean eon than it is today. The mantle contained large amounts of residual heat from planetary formation and radioactive decay. This heat drove vigorous convection within the mantle. Hot material rose toward the surface, while cooler material sank deeper into the planet. These movements influenced volcanic activity and crust formation. Large volumes of magma reached the surface, creating new crustal material. The interaction between rising magma and existing rock contributed to the constant reshaping of the planet's outer layers. The question of when plate tectonics began remains one of the major topics in Earth science. Modern Earth is characterized by moving tectonic plates that interact through processes such as subduction, collision, and seafloor spreading. During the Hadean eon, conditions were different because of the high temperatures within the mantle. Some scientists suggest that plate tectonics may have begun during the late Hadean. Others scholars argue that different forms of crustal movement operated before the modern tectonic system developed. Evidence remains limited because so little Pleiadian crust survives. Nevertheless, many researchers believe that important geological processes responsible for shaping modern Earth may have originated during the same period. The young sun also influenced conditions on Earth. During the Hadrian Eon, the sun was somewhat less luminous than it is today. Despite this lower brightness, Earth remained warm enough to support liquid water. Scientists continue to investigate how this occurred. Greenhouse gases in the atmosphere likely played a significant role by trapping heat and maintaining temperatures above the freezing point of water. Solar radiation affected atmospheric chemistry in many ways. Without a protective ozone layer, ultraviolet radiation reached the surface more easily than it does today. Chemical reactions driven by sunlight occurred throughout the atmosphere and may have contributed to the production of various compounds important for later stages of Earth's development. The interaction between the atmosphere, oceans, crust and interior created a highly dynamic planetary system. Water participated in chemical reactions with rocks. Volcanic gases entered the atmosphere and dissolved into oceans. Minerals formed and altered under changing environmental conditions. These processes gradually transformed Earth's surface and chemistry. Hydrothermal systems may have been common during the Hadrian Eon. When water interacted with hot rock and magma, heated fluids circulated through cracks and fractures in the crust. These systems transported minerals and chemical compounds between different regions. They also created environments with unique chemical conditions. Many scientists consider hydrothermal systems important because they may have contributed to the complex chemistry that eventually preceded life. Although direct evidence from the Hadrian Eon remains scarce, geological processes capable of supporting such systems were likely widespread. The magnetic field may also have begun developing during this early stage of Earth's history. The movement of molten metal within the core generates Earth's magnetic field through a process known as the geodynamo. Evidence suggests that some form of magnetic field may have existed more than 4 billion years ago. A magnetic field provides protection against charged particles originating from the Sun. By deflecting much of this radiation, it helps preserve the atmosphere and protect surface conditions. The timing and strength of Earth's earliest magnetic field remain subject of ongoing research, but its development was an important aspect of planetary evolution. Throughout the Hadrian Eon, Earth experienced continual transformation. New crust formed while older crust disappeared. Volcanoes released gases that shaped the atmosphere. Rainfall contributed to the formation of oceans. Impacts altered landscapes and influenced planetary chemistry. Internal heat drove geological activity on a massive scale. The conditions present during this period established many of the foundations upon which later geological and biological developments would occur. The formation of the core, mantle, crust, atmosphere, oceans and magnetic field all trace important parts of their history to this early stage. Although the Hadrian Earth was extremely different from the modern planet, many of the fundamental systems that characterize Earth today began developing during these ancient millions of years. By the end of the Hadrian Eon, the planet had changed substantially from the molten world that emerged from planetary formation. Significant cooling had occurred in many regions. Oceans were present across parts of the surface. Crustal materials had become more established. Atmospheric processes had become increasingly complex. Geological activity remained intense, yet Earth had already begun evolving towards the conditions that would characterize the following eon, known as the Archean. The Hadrian Eon therefore represents the earliest known stage of Earth's existence, a time when the planet was still being assembled, heated, reshaped, and chemically transformed. Every major component of the Earth system was undergoing development. The interior remained active, the surface remained unstable, the atmosphere continued evolving, and the oceans were beginning to influence planetary processes. Vast amounts of energy flowed through the young world as volcanic eruptions, impacts, crust formation, chemical reactions, and internal convection worked together to shape the planet's earliest outer environment. The early state of Earth involved extremely high temperatures across its outer layers, with materials present in liquid and partially vapor forms due to intense energy released during formation. This stage began around 4,500,000,000 years ago, when the planet was still forming from surrounding material in space. During this period, solid ground was not stable in most regions, and molten rock dominated the surface environment. The internal structure of Earth was also developing as heavier materials moved toward the center, and lighter materials moved toward outer layers. This internal movement influenced heat distribution throughout the planet. As time continued, energy from radioactive substances inside Earth contributed to sustained heating. These substances released energy steadily and affected the condition of rocks and minerals. At the same time, impacts from objects in space added additional energy to the surface and interior. Each impact released heat into surrounding regions of rock and vaporized existing surface materials. This continuous energy input kept most surface regions in a molten state for long periods. The surface environment contained large quantities of molten rock that moved slowly under the influence of internal motion. This molten material formed a continuous layer in many regions. Beneath this layer, movement of denser material toward the center created a core structure composed primarily of iron and nickel. This separation of materials influenced heat flow within the planet. Heat from deeper regions moved upward towards the outer layers, maintaining high temperatures across surface environments. During this stage, gases were released from molten rock. These gases included water vapor, carbon dioxide, nitrogen, and other volatile substances. The release of gases occurred through volcanic activity across many areas of the planet. These gases accumulated around the planet and formed an early atmosphere. This atmosphere contained high amounts of heat energy, which prevented condensation of water in early stages. As internal heating continued, the surface of Earth remained in a molten state across large regions. The movement of molten material allowed mixing of chemical elements. Silicate materials formed the main component of the molten surface. Iron-rich materials continued to move downward toward the central region. This movement created distinct internal layers that affected later cooling processes. Over time, energy loss from the surface into surrounding space began to influence temperature conditions. The outermost layer of molten material started to lose heat gradually. This loss of heat occurred through radiation into space. As heat left the outer layers, certain regions began to form thin, solid crust segments. These solid segments were unstable at first, and often broke apart due to ongoing internal movement. The formation of early solid crust occurred in isolated areas where temperature reduction allowed minerals to crystallize. These crystals formed structures that remained solid for limited periods before being remelted in many cases. The repeated formation and destruction of early crust segments contributed to gradual stabilization of outer layers. These processes occurred over long durations, with continuous interaction between molten material and forming solid surfaces. Water vapor present in the early atmosphere played an important role in later surface changes. as temperature levels decreased in water regions, water vapor began to condense into liquid form. This condensation process occurred when atmospheric conditions allowed transition from vapor to liquid. The liquid water formed began to fall towards the surface as precipitation. This precipitation accumulated in lower areas of the planet where surface depressions existed. These accumulating liquid water deposits formed early bodies of water. The initial formation of these bodies occurred in regions where surface temperatures allowed liquid stability. Over time, these water bodies expanded as continued precipitation added more liquid water. Volcanic activity also contributed additional water vapor to the atmosphere, which later condensed and added to surface water accumulation. The interaction between a cooling crust and accumulating water influenced surface conditions significantly. Water interacted with newly formed solid rock, leading to chemical changes in surface materials. Minerals present in the crust underwent alteration due to prolonged contact with liquid water. These changes contributed to development of more stable surface regions in certain areas. As cooling continued, the thickness of solid crust increased in some regions. This increase occurred as more molten material solidified beneath cooler surface conditions. The solid crust eventually formed a more continuous layer, although movement beneath this layer remained active. This movement caused fracturing and reformation of crustal sections over long periods. Water bodies continued to gather and spread across surface depressions. These depressions filled gradually as precipitation vents continued. Additional water was introduced through volcanic outgassing, where internal heat released water vapor trapped in rocks. This vapor condensed and contributed further to surface water levels. The Earth atmosphere remained dense with gases released from the volcanic activity. These gases maintained pressure conditions around the planet and influenced temperature behavior at the surface. Over time, as cooling progressed, some gases began to react with surface materials and dissolve into forming water bodies. This interaction altered the composition of both atmosphere and water. Carbon dioxide present in the atmosphere dissolved into liquid water in significant amounts. This dissolution affected chemical conditions within early oceans. Dissolved gases participated in chemical processes that modified water composition. Nitrogen remained present in the atmosphere and contributed to its long-term stability. The formation of oceans occurred through continuous accumulation of liquid water over extended periods. Water collected in low-lying regions where gravity directed flow of liquid from higher elevations. These regions became stable collection points for water, allowing gradual expansion of early oceans. The depth of these water bodies increased as more precipitation occurred and more vapor condensed. The cooling of Earth's surface allowed greater stability of liquid water on the planet. Temperature conditions gradually reached levels where liquid water remained present for extended periods without rapid evaporation. This stability supported expansion of oceanic regions. Water circulation began to occur through movement driven by temperature differences and surface interactions. Volcanic activity continued during this time, releasing both heat and gases into the environment. This activity influenced both atmosphere and ocean composition. Submarine volcanic activity introduced additional materials directly into forming ocean basins. These materials interacted with water and contributed dissolved minerals to ocean systems. The early oceans contained dissolved salts and minerals derived from rock interaction. Water continuously interacted with basaltic surfaces, extracting chemical components. The These components accumulated in ocean water over time. This process contributed to the chemical development of early marine environments. As crust formation progressed, solid rock layers became more extensive across the planet. These layers formed through repeated cooling of molten material. The crust remained subject to internal movement due to ongoing heat beneath it. This movement caused deformation of surface structures and reshaping of ocean basins. Water circulation within early oceans included movement driven by temperature variation and planetary rotation. These movements distributed heat and dissolved materials throughout ocean regions. Circulation patterns influenced the distribution of chemical substances within water bodies. The atmosphere above early oceans continued to change composition over time. Carbon dioxide levels decreased gradually as more gas dissolved into water and reacted with surface materials. Water vapor levels adjusted according to temperature conditions. These changes influenced precipitation patterns and continued growth of ocean systems. Rainfall continued to contribute water to ocean basins. Each cycle of evaporation and condensation moved water between atmosphere and surface. This movement supported continuous replenishment of ocean water. Volcanic emissions also contributed additional water vapor into atmospheric systems, reinforcing the cycle of condensation and precipitation. The interaction between water and rock extended into deeper regions of crustal material. Chemical reactions occurred where water penetrated cracks in solid rock. These reactions altered mineral structures and contributed to long-term changes within crust composition. These processes occurred steadily over long durations. As cooling progressed further, surface temperatures reached conditions where more extensive, solid crust could persist without frequent melting. This allowed larger stable regions of land and ocean to develop. The distribution of these regions continued to change due to internal movement and surface processes. Ocean basins expanded as crustal structures adjusted under internal forces. These basins collected increasing amounts of water. Water depth increased in many regions as accumulation continued. The interaction between crustal movement and water accumulation shaped surface features. Volcanic islands formed where molten material reached the surface through cracks in the crust. These islands interacted with surrounding water, releasing heat and materials into ocean systems. Surrounding water influenced cooling of volcanic structures, affecting their shape and stability. Chemical processes within oceans included continuous interaction between dissolved minerals and water molecules. These processes led to gradual changes in ocean composition. Elements such as sodium, calcium, magnesium, and chlorine became part of ocean water through prolonged interaction with rocks. The early Earth environment during cooling included continuous energy exchange between interior and exterior regions. Heat from the interior moved toward the surface, while energy was lost into space. This movement influenced temperature distribution across the planet. Solid crust formation continued as temperature levels allowed more widespread solidification of surface materials. These solid layers formed in overlapping sections that connected over time. The crust remained dynamic due to internal heat and movement beneath it. Water accumulation in ocean basins increased as atmospheric conditions allowed sustained precipitation. Liquid water remained stable in surface depressions for long durations. Ocean systems expanded as additional water became available through atmospheric and volcanic sources. The early oceans played a role in modifying atmospheric composition. Dissolved gases reduced atmospheric concentrations of certain substances. This interaction influenced long-term stability of atmospheric structure. Water and gas exchange continued between ocean and atmosphere. Mineral deposition occurred in ocean environments as dissolved substances reached saturation levels. These minerals settled on ocean floors, forming layers of sediment. This process occurred continuously as chemical balance shifted in water systems. Temperature variation across the planet decreased gradually, as internal heat distribution changed and surface cooling continued. This allowed more stable conditions for liquid water and solid rock to exist simultaneously across the planet. Ocean and crust systems became more established under these conditions. The movement of tectonic structures began to influence ocean basin shapes. Crustal sections shifted slowly due to internal forces. These movements affected distribution of land and water. Ocean regions adjusted in response to these structural changes. Water continued to cycle between atmosphere and surface through evaporation and precipitation. This cycle maintained continuous movement of water across planetary systems. Volcanic activity continued to release water vapor and gases into the atmosphere, sustaining the presence of atmospheric moisture. Chemical interactions within oceans influenced formation of complex mineral structures. These structures accumulated on ocean floors and interacted with surrounding water. Ocean chemistry evolved gradually as interactions continued over extended periods. The cooling process of Earth involved gradual reduction of internal heat, flow towards the surface. This reduction allowed increased stability of solid and liquid phases on the surface. Ocean systems expanded in response to these stable conditions. Surface regions became more defined as solid crust, and liquid water persisted over long durations. Ocean basins retained water through gravitational convection and continuous replenishment. These systems remained active under ongoing internal geological processes. The early Earth environment maintained continuous interaction between heat, rock, water, and gas. These interactions influenced the formation and expansion of oceans and the stabilization of surface conditions. The origin of the first simply life forms refers to the long process through which non-living matter on the early Earth gradually organized into living systems. This process took place on young Earth after its formation, when the surface was still changing and the environment was very different from what exists today. At that time, the planet had strong volcanic activity, frequent changes in surface conditions, and a developing atmosphere that contained gases released from the interior of the Earth. The oceans were forming as water vapor cooled and condensed over long periods, filling low areas on the surface. These early oceans became important locations where many chemical reactions could take place over extended periods. The materials present on the early Earth included simple gases, such as hydrogen, methane, ammonia, water vapor, carbon dioxide, and nitrogen. These gases interacted under energy sources that were present in the environment. Energy came from volcanic heat, electrical discharges from storms, ultraviolet radiation from the sun, and heat from impacts of space objects. These energy sources caused chemical reactions among simple molecules, leading to the formation of more complex organic molecules. Organic molecules are carbon-based compounds that form the basis of living structures. In the early oceans and shallow water environments, simple molecules dissolved and moved freely. Over time, repeated energy input allowed these molecules to combine into larger and more complex forms. Among the important molecules formed were amino acids, which are the basic units needed to build proteins. Proteins are essential for many biological functions in living systems. The formation of amino acids in early Earth conditions showed that basic components of life could arise from non-living chemical substances when the right conditions are present for long periods. Other important organic compounds included simple sugars and nitrogen-containing bases. These molecules also formed under early Earth conditions and became part of more complex structures later. These compounds could accumulate in certain environments where water evaporation, temperature changes, and mineral surfaces supported chemical concentration. Mineral surfaces, especially those found in clay and rocky layers, helped bring molecules together and provided places where reactions could continue over time. As organic molecules accumulated, some began to form chains and networks. These chains included long sequences of carbon-based structures that could hold chemical information or perform basic chemical functions. Among these structures, ribonucleic acid played an important role in early life development. Ribonucleic acid molecules can store information and also assist in chemical reactions. The presence of such molecules suggests that early life processes may have involved systems where one type of molecule carried both information and functional activity. In water environments, some organic molecules naturally formed small enclosed structures. These structures were made when fatty molecules organized themselves into spherical shapes with an outer boundary that separated the inside from the outside environment. These enclosed structures allowed different chemical conditions inside compared to the surrounding water. Inside these structures, reactions could occur in a more controlled way because molecules could be held together in limited space. Over time, some of these enclosed molecular structures became more stable. They could grow by absorbing additional molecules from the surrounding environment. Some of them could also divide into smaller structures when they reached a certain size or when environmental conditions changed. This division allowed chemical systems inside these structures to continue existing in multiple forms. These early structures are considered important steps toward the development of the first simple life forms. Inside these structures, chemical reactions continued to develop. Some molecules began to influence the production of other molecules. This led to chemical networks where certain reactions supported other reactions. In such systems, molecules that could help maintain the stability of the structure became more common over time. These chemical networks became more organized through repeated cycles of formation and breakdown in changing environmental conditions. Water played a central role in these processes. It acted as a medium where molecules could move, mix, and interact. It also allowed temperature changes to influence chemical reactions. In warm environments, molecules moved more actively and reacted more frequently. In cooler environments, molecules became more stable and remained in certain forms for longer periods. These variations in conditions supported the gradual development of more complex chemical systems. The early Earth environment also included areas with strong chemical gradients. These gradients involved differences in concentration of substances, such as hydrogen ions and other charged particles. These differences created conditions where energy could be used to drive chemical reactions. In such environments, molecules could be pushed into new forms through continuous chemical activity. Certain mineral-rich environments provided surfaces where molecules could attach and interact. These surfaces helped organize molecules into structured arrangements. When molecules were arranged in specific ways, they could react more efficiently with each other. This allowed the formation of longer chains of organic compounds and more stable chemical networks. These networks could continue to develop as long as energy and raw materials were available. The development of self-coupling molecules played a key role in the origin of early life. Some molecules have the ability to make copies of themselves using nearby chemical building blocks. When a molecule could produce similar copies, variations could occur during the coupling process. Some variations allowed certain molecules to persist longer or function more effectively in the environment. This led to an increase in molecules that could maintain their structure and continue producing copies over extended periods. The presence of self-copying chemical systems allowed information to be stored and transmitted across generations of molecular structures. This created continuity in chemical processes. Over time, systems that could maintain and transfer information became more stable in the environment. These systems also interacted with surrounding molecules, leading to increasing complexity in chemical organization. Energy transfer was important in maintaining these chemical systems. Energy from the environment allowed reactions to continue and supported the formation of new molecular bonds. Without continuous energy input, many of these reactions would not have been sustained. The early Earth provided multiple sources of energy that operated over long periods, allowing chemical systems to develop gradually. As chemical systems became more organized, they began to show characteristics that are associated with living processes. These included the ability to maintain internal chemical conditions different from the outside environment, the ability to grow through addition of new molecules, and the ability to produce copies of internal chemical structures. These characteristics developed gradually through continuous chemical changes. The formation of early membranes was also important. Membranes formed from simply lipid molecules that naturally arranged themselves in water. These membranes created boundaries that separated internal chemical environments from external surroundings. Inside these boundaries, chemical reactions could be maintained in a more stable manner. This separation allowed different chemical conditions to exist inside and outside the membrane, supporting more organized reactions. Within these membrane-bound structures, chemical reactions became more coordinated. Molecules that could assist in maintaining structure or supporting reproduction of chemical systems became more common. These systems gradually developed internal cycles of chemical activity that were maintained through repeated reactions. These cycles allowed continuous transformation of molecules within enclosed environments. The early Earth contained many environments where these processes could occur. Shallow water areas, mineral-rich surfaces, geothermal regions, and other chemically active locations provided conditions where organic molecules could accumulate and react. Each of these environments contributed to different aspects of chemical development, supporting the gradual organization of simple molecules into more complex systems. Some chemical systems developed the ability to respond to changes in their environment. When conditions changed, certain molecules could adjust their activity or stability. This ability to respond allowed chemical systems to persist through variations in temperature, chemical availability, and energy input. Systems that could maintain their structure under changing conditions continued to exist for longer periods. Over long periods, chemical networks became more interconnected. Molecules that participated in multiple reactions helped link different processes together. These connections allowed energy and materials to move through chemical systems in organized ways. This organization supported the continuation of chemical cycles within enclosed structures. The formation of early informational molecules also influenced the development of simple life forms. Molecules that carried sequences of chemical instructions could influence the production of other molecules. These sequences allowed chemical systems to maintain patterns over time. When changes occurred in these sequences, variations in chemical activity followed. leading to diversity in molecular structures. The gradual accumulation of these processes led to systems that were able to maintain themselves for extended periods. These systems relied on continuous chemical reactions, energy input, and material exchange with the environment. The stability of these systems depended on the balance between formation and breakdown of molecular structures. In aquatic environments, movement of water helped distribute molecules across different regions. This movement allowed mixing of substances and spread of chemical materials. It also allowed different environments to interact chemically over time. Through these interactions, chemical diversity increased and new molecular arrangements became possible. Certain regions of the early Earth may have experienced repeated cycles of drying and wetting. These cycles influenced the concentration of molecules. When water levels decreased in certain areas, molecules became more concentrated and reacted more frequently. When water returned, molecules dispersed and continued interacting in broader environments. These cycles supported ongoing chemical changes. The gradual development of organized chemical systems continued through long periods of environmental activity. Chemical structures became more stable, more coordinated, and more capable of maintaining internal reactions. These developments formed the basis for systems that can persist, grow, and reproduce in chemical form. The transition from non-living chemistry to early biological systems involved continuous changes in molecular organization. Chemical networks became increasingly structured, allowing more efficient use of available energy and materials. These processes occurred through repeated interactions between molecules, energy sources, and environmental conditions. Some molecular systems developed mechanisms that helped maintain internal stability. These mechanisms involved cycles of reactions that balanced production and breakdown of molecules. Such balance allowed systems to persist in changing environments without losing their internal organization. The environment of the early Earth provided continuous conditions for chemical change. Volcanic activity released gases, water bodies, circulating materials, and energy from external sources supported ongoing reactions. These factors combined to sustain chemical activity over long durations. Molecular structures that were able to persist in these conditions became part of continuing chemical systems. These systems maintained their organization through repeated cycles of chemical transformation. Over time, these systems developed increasing levels of internal structure and functional organization. As chemical organization progressed, some systems developed more efficient ways of using available resources. Molecules that supported stability and reproduction of chemical patterns became more widely present in these systems. This led to increasing continuity in molecular structures across different environments. The gradual progression of these processes formed the basis for early, simply life forms. These forms were not fully developed biological organisms, but represented organized chemical systems capable of maintaining structure, processing energy, and producing copies of internal components through chemical reactions. The period known as the Archean Eon refers to a very long stage in the early history of Earth that took place around 4 billion years ago to around 2,500,000,000 years ago. During this vast span of time, Earth was undergoing major internal and surface changes. The crust was still forming and reshaping, volcanic activity was widespread, and the atmosphere and oceans were still developing their own forms. The conditions on the planet were very different from later times, and the surface environment was continuously changing due to heat from the interior of the Earth and impacts from space objects. The rocks from this period preserve rare and important evidence It helps explain how the earliest forms of life began and how they survived under conditions that were unstable and constantly shifting. The study of this time also involves understanding how simple living systems appeared in water environments and how they slowly became more established across different parts of the early oceans. During the early part of this era, the surface of the Earth was not yet stable in the way it is in later times. The crust existed in small sections that were constantly breaking, forming again, and being reshaped by heat from below. Magma moved upward, frequently, forming new rock layers that cooled quickly at the surface before being changed again by new heat movements. Large areas of the surface were covered by molten material, while other regions cooled enough for solid rock to exist for short periods before being altered again. The atmosphere during this time contained gases released from volcanic activity, including water vapor, carbon dioxide, nitrogen, and small amounts of other gases. Oxygen in free form was extremely limited in the atmosphere at this stage, which meant that chemical reactions occurring in the air and in water were different from those in later periods. Rainfall began to fall as the planet cooled in certain regions, and this water collected in surface depressions to create the earliest oceans. These early oceans were not stable bodies at first, but changed in size, temperature, and chemical composition as volcanic activity continued. The early oceans of the Archean eon became important environments for chemical reactions that supported the formation of simple organic compounds. These compounds formed from elements such as carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur that were present in water and dissolved gases. Energy sources such as heat from volcanic vents, ultraviolet radiation from the sun, and electrical activity from storms contributed to chemical changes in these compounds. Over time, simple molecules began to combine into larger and more complex structures. Some of these structures had the ability to maintain stability for short periods in water environments. The oceans contained many regions where temperature differences and chemical gradients allowed repeated cycles of formation and breakdown of these compounds. These cycles played a role in the gradual development of systems that could store information and carry out basic chemical processes in a more organized way than earlier random reactions. The earliest forms of microbial life appeared in this environment within the Archean eon. These life forms were extremely simple in structure and were not visible to the naked eye. They existed as single-cell organisms that carried out basic functions needed for survival, including taking in substances from the surrounding water and releasing waste materials. These organisms did not contain complex internal structures found in later life forms. Their biological systems were based on simple chemical reactions that allowed them to maintain stability and reproduce under suitable conditions. The first microbial life likely developed in aquatic environments where conditions were less harsh compared to exposed land surfaces. Deep ocean environments, shallow pools, and areas near underwater volcanic activity provided chemical energy sources and stable surroundings that supported the persistence of these early organisms. In the oceans of this time, microbial life gradually spread into different environments where conditions allowed survival. Some microorganisms live near hydrothermal vents on the ocean floor where hot water rich in dissolved minerals emerged from beneath the crust. These environments provided continuous energy sources and chemical nutrients that supported metabolic processes. Other microorganisms lived in shallow waters where sunlight could reach, allowing them to use light energy in simple ways. However, the atmosphere at that time did not contain high levels of oxygen, so many early microbial processes did not depend on oxygen for energy use. Instead, they used other chemical pathways involving sulfur, iron, and carbon-based compounds that were present in the surrounding water. These processes allowed microbial communities to remain active in environments that would not support more complex forms of life. The development of microbial life during the Archean eon involved long periods of gradual change, in which chemical systems became more organized. Simple organic structures present in water environments sometimes combined into arrangements that could perform repeated chemical cycles. These cycles included the ability to absorb molecules, convert them into different forms, and release byproducts into the surrounding environment. Over time, certain molecular systems became more stable and more efficient in maintaining their structure during these cycles. This stability allowed them to persist for longer periods in changing environmental conditions. The early biological systems did not have defined cells at first, but gradually membrane-like structures formed around chemical systems, helping to separate internal reactions from the surrounding environment. This separation allowed greater control of chemical processes inside these early forms of life. As microbial life continued to exist in the oceans, different types of metabolic activity began to appear. Some organisms used dissolved carbon compounds as a source of energy, while others used sulfur compounds or iron compounds. The availability of these chemical sources depended on volcanic activity, water circulation, and interaction between rocks and seawater. In certain environments, microbial communities formed layers on surfaces such as rocks or sediments. These layers contained groups of microorganisms that carried out different chemical processes within close proximity. Waste products from one type of microbial activity could become useful inputs for another type of microbial activity, creating a continuous flow of chemical exchange. These interactions helped maintain the presence of microbial communities in specific regions for long periods. In some parts of the oceans, microbial activity led to the formation of layered structures in sediments. These structures formed when microorganisms grew on surfaces and trapped particles from surrounding water. Over long periods, repeated growth and sediment accumulation created visible formations in rock records. These formations provide evidence of microbial life during the Archean eon, and show how microbial communities were able to persist in different environmental conditions. The chemical processes carried out by these organisms also influenced the composition of the surrounding water and sediments. Substances produced by microbial metabolism gradually changed local chemical conditions, allowing new types of reactions to occur. The early Earth atmosphere during this time contained very little free oxygen, which affected the types of chemical reactions that could occur both in the atmosphere and in the oceans. Many microbial organisms developed processes that did not rely on oxygen. Some of these processes produced methane, hydrogen or other gases that entered the atmosphere. These gases contributed to changes in atmospheric composition over time. The interaction between microbial activity and atmospheric chemistry created slow changes in environmental conditions. As microbial populations increased in certain regions, their metabolic activities had a noticeable influence on local chemical balances in water and sediment environments. The surface of the Earth during the Archean eon also experienced frequent volcanic eruptions and impacts from space objects. These events released large amounts of energy and material into the environment. Despite these disturbances, microbial life continued to exist in protected environments such as deep oceans and underground water systems. In these locations, temperature conditions were more stable, and chemical sources remained available even when surface conditions changed rapidly. The ability of microbial life to persist in these environments depended on simple metabolic systems that could operate under a wide range of chemical conditions. Some microorganisms were able to survive in environments with high temperatures near volcanic vents, while others lived in cooler regions of the ocean. The oceans contained dissolved minerals and gases that interacted with microbial processes. Iron and sulfur compounds were especially important in many early metabolic systems. These compounds circulated through water and sediments due to volcanic activity and chemical reactions with rocks. Microbial communities used these compounds in energy-producing reactions that supported growth and reproduction. The interaction between microbial activity and mineral chemistry contributed to changes in sediment composition over time. As sediments accumulated on the ocean floor, they preserved traces of microbial activity, including chemical signatures and structural formations. Within the Archean Eon, microbial life gradually became more widespread in ocean environments. Different regions of the ocean supported different types of microbial communities, depending on temperature, chemical composition, and availability of energy sources. Some communities existed in nutrient-rich areas near volcanic activity, while others existed in more stable open ocean regions where chemical conditions changed slowly. The presence of microbial life influenced the cycling of elements such as carbon, sulfur, and iron within the oceans. These cycles involve repeated movement of elements between water, sediments, and microbial organisms. The chemical evolution that supported microbial life also involved the gradual development of systems capable of storing and transferring information. Early molecular systems that played a role in replication became more stable over time, allowing more reliable reproduction of chemical structures. These systems enabled continuity of biological processes across generations of microbial organisms. The development of information-carrying molecules allowed biological processes to become more organized, even though the structures involved remained very simple. These molecular systems interacted with surrounding chemical environments in ways that supported ongoing cycles of growth and replication. The early Earth environment during this time continued to change slowly as internal heat decreased and the crust became more stable in certain regions. Ocean environments expanded and became more persistent over long periods. Microbial life continued to exist within these environments, adapting to available chemical and physical conditions. Sedimentary deposits accumulated in different parts of the ocean floor, preserving evidence of biological activity. These deposits include chemical patterns that reflect metabolic processes carried out by early microorganisms. The distribution of these deposits provides information about where microbial life existed and how it interacted with its environment. As the Archean Eon progressed, microbial ecosystems became more established in ocean environments. Chemical cycles involving carbon, sulfur, iron, and other elements became increasingly influenced by biological activity. Microorganisms participated in transformations of these elements through metabolic processes that operated continuously in suitable environments. These processes affected both local and broader environmental conditions over long periods. The interaction between biological systems and geological processes created patterns of chemical change that became recorded in rocks formed during this time. The study of microbial life in this period involves examining fossil evidence, chemical traces, and geological formations that remain preserved in ancient rocks. These records show that life existed in simple forms very early in Earth's history, and that these forms were able to persist under a wide range of environmental conditions. The chemical signatures found in ancient rock formations provide evidence of metabolic activity and biological processes that occurred in ocean environments. These signatures include variations in element distribution and isotopic patterns that reflect biological influence on chemical cycles. During this long period of Earth's history, microbial life remained closely connected to water environments. Oceans provided the main setting where chemical reactions supporting life could continue over long periods. The interaction between water, minerals, and biological systems created continuous cycles of chemical change. These cycles allowed microbial communities to remain active in different regions of the planet. The distribution of microbial life depended on the availability of energy sources and chemical compounds in surrounding environments. Some regions supported high levels of microbial activity due to constant input of volcanic materials, while other regions supported slower but stable microbial processes. The environmental conditions of the Archean eon included ongoing changes in temperature, atmospheric composition, and ocean chemistry. Microbial life responded to these changes through variations in metabolic activity and distribution. Some microorganisms were able to adjust to changing chemical conditions by using different metabolic pathways depending on availability of resources. These adaptations allowed microbial communities to remain present across a wide range of environments. The interactions between microbial processes and environmental changes contributed to gradual shifts in ocean chemistry and sediment composition over long periods of time. The rise of photosynthesis and oxygen production marks a major shift in the long development of life on Earth. It describes a time when living cells began to use sunlight to change simple materials into energy-rich substances that help them live and grow. This process also led to the release of oxygen into the air and water. Over a long period of time, this change altered the nature of the oceans, the atmosphere, and the conditions that supported life. The earliest forms of life on Earth were simple and microscopic. They lived in water and depended on chemicals already present in their surroundings. These early organisms did not use oxygen for energy. Instead, they relied on chemical reactions that did not involve oxygen. At that time, the atmosphere contained very little oxygen, and most environments were filled with gases such as carbon dioxide, nitrogen, water vapor, and other volcanic gases. Photosynthesis began when certain microscopic organisms developed the ability to use sunlight as an energy source. These organisms were among the earliest forms of bacteria. They lived in oceans where sunlight could reach shallow waters. Sunlight provided a constant source of energy that could be used to change carbon dioxide in water into energy-rich compounds inside of cells. During this process, oxygen was released as a waste product. This release of oxygen was not immediately useful to most young organisms because many of them could not tolerate oxygen. Oxygen was chemically active and could damage molecules inside cells that were not adapted to handle it. The early photosynthetic organisms likely lived in warm oceans filled with dissolved minerals and gases. These organisms spread across many shallow water environments where sunlight was available. Their activity continued over a very long time and oxygen gradually began to accumulate in the surrounding water. At first, much of this oxygen reacted with dissolved iron and other substances in the oceans. This caused chemical changes in the water, forming new mineral compounds that settled on the seafloor. Only after many chemical reactions took place did oxygen begin to remain in the water in larger amounts. As oxygen levels slowly increased in the oceans, some oxygen began to move into the atmosphere. The atmosphere at that time was still mostly made up of gases that did not support oxygen-based life. The gradual addition of oxygen into the air created new chemical conditions. Oxygen in the atmosphere reacted with gases and surface materials on Earth. These reactions continued for long periods, changing the composition of the air. Even though oxygen was present, it was still not dominant in the atmosphere during the early stages of this process. Photosynthetic organisms continued to develop and spread. Some of them became more efficient at capturing sunlight and using it to produce energy. These organisms used structures inside their cells that contained pigments capable of absorbing light. The absorbed light energy was used to drive chemical reactions that converted carbon dioxide and water into sugars and other compounds needed for growth and survival. Oxygen was released continuously as part of this process. The ongoing activity of these organisms created a steady source of oxygen entering the environment. Over time, large amounts of oxygen entered both the oceans and the atmosphere. The accumulation of oxygen led to changes in many chemical cycles on Earth. Iron that had been dissolved in oceans reacted with oxygen and formed solid particles. These particles accumulated in layers on the ocean floor. This process continued repeatedly, forming thick deposits over long periods. The presence of oxygen also changed the chemistry of other elements in the ocean's atmosphere. Photosynthetic organisms lived in groups called microbial mats in many shallow water environments. These mats contained layers of cells that worked together to capture sunlight and carry out chemical reactions. The upper layers received the most sunlight, while deeper layers received less. Despite these differences in light exposure, the organisms within these mats continued to function as part of a connected system. The oxygen released by these organisms moved into the surrounding water and eventually into the air. The buildup of oxygen in the atmosphere took a very long time. At first, oxygen levels remained low because most oxygen reacted with materials on Earth's surface. Rocks, minerals, and dissolved substances in oceans absorbed oxygen. Only after these materials became saturated with oxygen did free oxygen begin to remain in the atmosphere in greater amounts. This gradual process changed the structure of the atmosphere and created new conditions that affected living organisms. Some early organisms adapted to the presence of oxygen. These organisms developed internal systems that could use oxygen for energy production. Oxygen allowed more efficient energy release from food molecules. This new form of energy use supported more complex cellular structures. Organisms that used oxygen began to spread in environments where oxygen was present. At the same time, many organisms that could not tolerate oxygen remained in environments where oxygen levels were low. The presence of oxygen in the atmosphere also led to the formation of ozone in the upper layers of the atmosphere. Oxygen molecules were affected by solar radiation, leading to the creation of ozone molecules. Ozone absorbed harmful radiation from the sun and reduced its impact on Earth's surface. This change affected the conditions in surface environments and allowed organisms to exist in new regions over time. The formation of ozone was directly linked to the presence of oxygen produced by photosynthetic organisms. Photosynthesis continued to develop in different forms. Some organisms used different pigments that allowed them to capture light at different wavelengths. These variations allowed photosynthetic life to exist in a wide range of environments, including deeper waters and areas with different light conditions. Cyanobacteria became one of the most important groups of photosynthetic organisms in early Earth environments. Their activity contributed significantly to oxygen production over long periods. The continuous release of oxygen also influenced the chemical balance of oceans. Oxygen dissolved in water and interacted with various dissolved compounds. This changed the types of chemical reactions that could occur in marine environments. Some compounds became less stable in the presence of oxygen, while others formed more easily. These changes affected the availability of nutrients and the structure of microbial communities in the oceans. The energy captured through photosynthesis supported growth and reproduction in microbial populations. As populations increased, more oxygen was released into the environment. This created a feedback effect where more photosynthetic organisms led to more oxygen production, and oxygen levels influenced the distribution of different types of organisms. Some regions of the ocean had higher concentrations of photosynthetic activity due to better access to sunlight and nutrients. Over long periods, sediment layers formed on the ocean floor contained evidence of oxygen-related chemical processes. These layers recorded changes in the environment over time. The presence of iron-rich formations in ancient rocks reflects periods when oxygen reacted with dissolved iron in seawater. These formations show repeated cycles of oxygen production and chemical reaction in ocean systems. As oxygen became more abundant, it influenced the development of new metabolic pathways in living organisms. Cells that produce oxygen for energy production gained access to a more efficient way of breaking down food molecules. This allowed them to produce more energy for cellular functions. This change supported the development of more complex cell structures, including internal compartments that carried out specific tasks within the cell. Photosynthetic organisms were also developed protective mechanisms to manage the effects of oxygen being produced. Oxygen can be reactive and can damage cellular components if not controlled. Some organisms developed enzymes that helped manage oxygen levels inside their cells. These enzymes reduced harmful effects and allowed cells to continue functioning in oxygen-rich environments. The distribution of oxygen in Earth's atmosphere was not uniform during early stages. Some regions contained high levels of oxygen due to local biological activity, while other regions contained low levels. Ocean currents, atmospheric movement, and biological growth patterns influenced the distribution of oxygen over time. As photosynthetic activity expanded, oxygen spread into more areas of the planet. The interaction between sunlight, water, and carbon dioxide remained central to photosynthesis. Sunlight provided energy that drove chemical reactions inside cells. Water provided electrons and hydrogen atoms used in the formation of energy-rich compounds. Carbon dioxide provided carbon atoms used to build sugars and other organic molecules. Oxygen was released as part of the chemical process that rearranged these elements into new compounds. Photosynthesis also influenced global cycles of carbon. Carbon dioxide from the atmosphere and oceans was used by photosynthetic organisms. This reduced the amount of carbon dioxide in some environments and stored carbon in organic matter. When organisms died, their remains sometimes settled in sediments, where carbon became part of long-term geological deposits. This process influenced the movement of carbon through Earth's systems. The gradual increase in oxygen created conditions that allowed new forms of life to appear. Oxygen-supported metabolism allowed organisms to generate energy in ways that were not possible before oxygen became available. These changes supported the development of more diverse biological systems. Organisms adapted to different oxygen levels, leading to a wide distribution of life in various environments. Photosynthetic activity also responded to environmental changes. Variations in sunlight, nutrient availability, and water conditions influence the rate of photosynthesis. Organisms adjusted their activity based on these conditions. Some environments supported high levels of photosynthetic growth, while others supported lower levels. These differences affected local oxygen production rates. Over time, oxygen reached levels that influenced the chemistry of the entire atmosphere. Gases in the atmosphere interacted with oxygen, forming new compounds and changing atmospheric composition. This process continued over long periods, shaping the conditions that existed on Earth's surface. The presence of oxygen also influenced the stability of other gases in the atmosphere. The rise of photosynthesis and oxygen production involved many interconnected biological and chemical processes. Living organisms, sunlight, water, carbon dioxide, and Earth's surface materials all interacted continuously. These interactions took place over extremely long periods, during which gradual changes accumulated and altered the environment. The activity of microscopic organisms played a central role in shaping the conditions of the planet. Photosynthetic organisms remained active in many aquatic environments. Their ability to capture sunlight and release oxygen continued to influence both local and global systems. The presence of oxygen affected the structure of microbial communities, the chemistry of oceans, and the composition of the atmosphere. These changes continued without interruption across vast spans of time, shaping the environment in which life existed and continued to develop. The Great Oxygenation Event was a major change in Earth's long history, when large amounts of oxygen began to build up in the air and in the oceans. This change happened during the early part of Earth's history, when simple life forms were already present in the oceans. Before this time, the atmosphere of Earth had very little oxygen gas. The air was mostly made up of gases, such as nitrogen, carbon dioxide, water vapor, and other gases released from volcanic activity. Oceans also contained many dissolved materials, especially iron in its reduced form. Life at that time existed mainly as simple, single-celled organisms that lived in water and did not use oxygen for energy. The rise of oxygen began with tiny living organisms called cyanobacteria. These organisms lived in oceans and had the ability to carry out photosynthesis. During photosynthesis, sunlight was used to change carbon dioxide and water into energy-rich substances that supported their growth. Oxygen was released as a waste product during this process. Over a very long time, these cyanobacteria increased in number across many shallow ocean environments. Their activity slowly introduced oxygen into the surrounding water. At first, the oxygen produced did not remain in the atmosphere. It reacted quickly with many substances in the oceans and on the surface of the planet. One of the most important reactions involved iron dissolved in seawater. The oxygen combined with the cyan and formed solid iron minerals. These minerals settled on the ocean floor in layers. Over long periods, these layers built up and became thick deposits, known in geological records. This process kept large amounts of oxygen from accumulating in the air during the early stages. As cyanobacteria continued to release oxygen, the available reactive materials in the oceans and surface environments gradually became limited. Once many of these materials were used up, oxygen began to remain in the water and later moved into the atmosphere. This shift marks the beginning of significant changes in the composition of Earth's air. The increase of oxygen in the atmosphere changed chemical conditions on the planet. The presence of oxygen in the atmosphere created new chemical reactions in surface environments. Many substances that had been stable under low oxygen conditions began to change. Rocks and minerals exposed to air experienced oxidation. where oxygen combined with elements such as iron and other metals. This process altered the composition of surface materials over long periods. The atmosphere itself became more reactive due to the presence of oxygen gas. The buildup of oxygen also affected living organisms that existed at the time. Many early life forms were adapted to environments without oxygen. These organisms used chemical processes that did not involve oxygen to obtain energy. When oxygen levels began to rise, these organisms experienced stress because oxygen can be harmful to biological structures that are not adapted to it. Some populations of organisms decreased in number or disappeared from certain environments. Other organisms remained in areas where oxygen levels were still very low, such as deep ocean environments and sediments. During this time, new forms of metabolism began to appear in some organisms. Certain life forms developed ways to use oxygen in energy-producing processes. Oxygen allowed more efficient release of energy from organic compounds. Organisms that adapted to use oxygen gained access to new ecological conditions in the changing environment. These developments marked an important shift in biological activity on Earth. The increase of oxygen in the atmosphere also led to the formation of a layer of ozone gas in the upper atmosphere. Oxygen molecules in the upper layers of the atmosphere were infected by solar radiation, which caused them to change and form ozone. This ozone layer absorbed a portion of incoming ultraviolet radiation from the sun. Before the presence of significant ozone, the surface of Earth was exposed to high levels of ultraviolet radiation. With the development of ozone, surface conditions changed in terms of radiation exposure. This allowed different environmental conditions to exist at the surface and in shallow waters. The change in atmospheric composition influenced the chemistry of oceans as well. Dissolved oxygen in seawater increased in certain regions. This affected chemical cycles involving carbon, sulfur, nitrogen, and iron. The balance of dissolved elements shifted as oxygen became part of many chemical reactions. Ocean chemistry became more complex as new reaction pathways became available. Sedimentary deposits from this time show clear evidence of changing oxygen conditions. Layers of iron-rich minerals formed in alternating patterns that reflect variations in oxygen availability over time. These layers are preserved in ancient rock formations and provide information about the gradual transition from low oxygen conditions to high oxygen conditions. The presence of these deposits indicates long periods of chemical change in ocean environments. The organisms living in shallow ocean environments experienced continuous environmental change during this time. Microbial communities adjusted their metabolic processes depending on local oxygen levels. Some microbes lived in surface waters where oxygen was present. Others lived in deeper regions where oxygen was still absent. This separation of environments allowed different biological processes to exist in different parts of the ocean system. The increase in oxygen also influenced the cycling of carbon in the environment. Organic material produced by living organisms began to interact with oxygen in new ways. Some organic compounds were broken down through reactions involving oxygen, which released carbon dioxide back into the environment. This created new pathways for carbon movement between living organisms, water, and the atmosphere. The chemical state of the atmosphere shifted slowly over a very long period. Oxygen levels increased in stages rather than in a single rapid change. Each stage involved periods where oxygen production and oxygen consumption were balanced in different ways. Volcanic gases, chemical reactions in oceans, and biological activity all contributed to the changing conditions. As oxygen continued to accumulate, the overall energy flow within ecosystems began to change. Organisms that used oxygen-based metabolism were able to extract energy from nutrients in a different way. This allowed changes in growth patterns and biological functions. Oxygen-based energy processes supported different cellular activities compared to earlier energy systems. The presence of oxygen also influenced the stability of certain gases in the atmosphere. Gases that were present in earlier atmospheric conditions reacted with oxygen and decreased in concentration over time. This changed the overall composition of the atmosphere and affected how gases moved between the surface and the air. Surface environments on Earth experienced chemical changes due to exposure to oxygen. Minerals on land surfaces reacted with oxygen in the air and formed new compounds. These processes altered the composition of soils and rocks exposed at the surface. Weathering processes became influenced by oxygen-driven reactions. The transition in atmospheric composition also affected ocean circulation patterns in terms of chemical distribution. Oxygen levels varied between different ocean regions depending on depth, temperature, and biological activity. These variations created zones with different chemical characteristics. Biological evolution during this period included changes in cell structures. Some organisms developed internal compartments that allowed better control of oxygen use within cells. This supported more complex energy systems. Other organisms maintained simpler structures and remained in environments with low oxygen levels. The accumulation of oxygen in the atmosphere marked a shift in the long-term chemical state of Earth's surface environment. Before this shift, reduced chemical conditions dominated many environments. After oxygen accumulation, oxidized conditions became more widespread. This change influenced almost every chemical process occurring at the surface, in oceans, and in the atmosphere. The activity of cyanobacteria remained central to these changes. Their continuous production of oxygen maintained a source of oxygen input into the environment. Over extended time periods, their activity shaped the chemical composition of both water and air. Their presence across wide ocean regions contributed to global scale changes. The interaction between biological processes and chemical reactions created a feedback system. Oxygen produced by living organisms altered environmental conditions, and those conditions influenced the distribution and activity of organisms. This ongoing interaction continued throughout the period of oxygen increase. The deposition of iron-rich layers in ocean sediments continued for long intervals. These deposits recorded changes in oxygen availability in marine environments. The alternating patterns in these layers reflect variations in biological activity, chemical reactions, and environmental conditions over time. As oxygen levels became more stable in the atmosphere, new environmental zones became established. Regions with high oxygen levels supported different forms of biological activity, compared to regions with lower oxygen levels. This variation influenced how organisms distributed themselves across marine and surface environments. The presence of oxygen also affected the solubility of certain elements in water. Some elements became less stable in dissolved form and formed solid compounds that settled in sediments. This changed the chemical composition of ocean water over time. The Great Oxygenation Event involved many interconnected processes that included biological activity, chemical reactions, atmospheric changes, ocean chemistry shifts, and long-term environmental transformation. These processes occurred over extended periods and influenced the structure of Earth's surface environment, the composition of air and water, and the development of early life systems. The appearance process of multicellular life is a long and gradual event in the history of Earth, and it happened after a very long time of single-celled life existing alone in the oceans and other water environments. Life began with single cells that carried out all basic functions inside one small structure. These early single cells were able to take in nutrients, respond to their surroundings, and reproduce by making copies of themselves. Over very long periods of time, these simple life forms spread across many environments on Earth and continued to change in smaller steps. The conditions on Earth also changed during these long periods, including changes in temperature, chemical content of water, and levels of gases in the atmosphere and oceans. These changes created new conditions in which life continued to develop in different directions. Multicellular life refers to living organisms made of more than one cell, where many cells exist together in one organism and carry out different roles. This form of life requires coordination between the cells, where cells must remain connected or work in a structured arrangement. Before multicellular life appeared, all organisms were single-celled and independent. Each cell performed all life functions on its own. Over a very long span of time, some single-celled organisms began to form simple groups. These groups were not yet fully organised multicellular organisms at first. The cells stayed close together after dividing, and some of them began to remain attached instead of separating completely. This created early forms of cell groups that stayed in clusters. In these early clusters, all cells still performed similar functions. There was not yet a strong division of roles. Each cell could still carry out basic processes needed for survival. As time continued, some clusters of cells began to show changes in behavior. Certain cells in the group began to take on different tasks compared to others. Some cells focused more on movement, while others focused more on processing nutrients. This separation of roles was a very important step in the development of multicellular life. The ability for cells to specialize allowed groups of cells to function in more organized ways. The environment of early Earth provided conditions that supported these changes. Oceans contained dissolved chemicals that were used by early organisms for energy and growth. These chemicals included simple compounds that formed through natural processes in the atmosphere and on the ocean floor. Energy sources such as sunlight and chemical reactions in deep ocean environments supported the activity of early life. Over long periods of time, these energy sources helped single-celled organisms survive and multiply, creating large populations spread across different regions of the oceans. As populations of single-celled organisms increased, interactions between cells also became more common. Some cells began to remain connected after reproduction due to small changes in their outer structures. The outer surface of cells played a role in holding cells together. In some cases, cells produced sticky substances that helped them remain attached. These substances were made of simple biological materials produced inside the cells. When cells stayed attached, they formed colonies that could remain stable in water environments. Inside these colonies, natural differences between cells began to appear. These differences were not planned or directed, but came from small variations in internal chemical activity. Some cells received more nutrients, while others received different amounts depending on their position within the colony. Cells that were located on the outside of the group had more direct contact with surrounding water. Cells inside clusters had less direct exposure to the environment. These differences influenced how cells behaved and how they developed over time. Over very long periods, genetic material inside cells also changed slowly. Genetic material controls how cells function and reproduce. Small changes in this material occurred during reproduction when cells made copies of themselves. These changes sometimes led to new traits in cells. Some traits made cells better and stay attached to each other. Other traits improved the ability of cells to share resources or respond to signals from nearby cells. When such traits appeared, they were passed on to new generations of cells. Communication between cells became an important factor in the development of multicellular life. Cells began to produce chemical signals that could be detected by nearby cells. These signals allowed cells to coordinate activities. For example, some cells could signal others to divide or to change their activity level. This form of communication was very simple at first, but it created a foundation for more complex coordination later. As signaling systems developed, groups of cells were able to behave in more organized ways. Cell division also played a major role in the formation of multicellular structures. When a single cell divided, the resulting cells sometimes remained attached instead of separating fully. Repeated divisions created larger clusters of cells. These clusters could grow in size while maintaining connections between cells. Over time, some clusters became more stable and organized. Stability allowed these groups to persist for longer periods in the environment. Different environments in the oceans supported different types of early multicellular development. Shallow waters contained more light, which supported organisms that relied on energy from sunlight. Deeper waters contained less light, but more chemical compounds released from the Earth's interior. These chemical compounds provided energy sources for organisms that did not rely on sunlight. In both environments, multicellular structures developed in different forms, based on available resources and conditions. As multicellular groups became more stable, the arrangement of cells within these groups became more structured. Some cells remained on the outer regions of clusters, while others remained in inner regions. Outer cells had more direct contact with environmental conditions, while inner cells were more protected. This separation of positions contributed to differences in function. Cells in different positions began to develop different roles based on their location and activity. Energy used within multicellular groups also became more organized. Cells within a group shared resources obtained from the environment. This sharing required movement of nutrients and chemical compounds between cells. Small channels and connections formed between cells, allowing substances to pass through. These connections made it possible for cells to support each other. When one group of cells obtained nutrients, those nutrients could be distributed to other cells within the same structure. Reproduction of early multicellular organisms also changed over time. Instead of a single cell separating from a group and living independently, entire groups of cells could reproduce together. In some cases, a group of cells could split into two groups, each continuing to grow and develop. In other cases, special cells within a group were responsible for reproduction. These reproductive cells could produce new groups of cells that developed into new organisms. The genetic instructions inside cells continue to influence how multicellular structures developed. Certain genes became active in some cells and inactive in others. This selective activity of genes allowed cells within the same organism to perform different roles. Some genes controlled movement, some controlled nutrient processing, and others controlled structural support. The regulation of gene activity was an important step in forming organized multicellular life. As multicellular organisms developed further, their structures became more stable and more complex in organization. Cells remained connected in consistent patterns. These patterns allowed organisms to maintain their shape and function over time. The arrangement of cells allowed for steady growth as new cells were added through division. Growth occurred in a controlled manner, where new cells joined existing structures without disrupting overall organization. Environmental pressures also influenced the development of multicellular life. Changes in temperature, availability of nutrients, and chemical composition of oceans affected which organisms survived and reproduced successfully. Organisms that could maintain stable internal conditions had better chances of survival. Multicellular structures allowed better control of internal conditions because different cells could manage different tasks. This internal organization helped maintain stable conditions within the organism. As time continued, more specialized cell types appeared within multicellular organisms. Some cells became responsible for protection, forming outer layers that shielded internal cells. Other cells specialized in absorbing nutrients from the environment. Some cells became involved in movement, allowing organisms to shift position in water environments. These specialized roles increased the ability of organisms to function in different conditions. The development of multicellular life also involved changes in how energy was used inside organisms. Energy obtained from the environment was distributed across many cells. This distribution required systems for transport and storage of energy-rich compounds. Cells developed mechanisms to store energy and release it when needed. These mechanisms allowed organisms to maintain activity even when external energy sources changed. Over long periods, multicellular organisms continued to diversify in structure and function. Some remained simple clusters of cells with limited specialization. Others developed more organized structures with distinct layers of cells. These layers performed different roles and worked together to maintain the organism. The presence of layers allowed more efficient distribution of nutrients and signals within the organism. Cell adhesion molecules played an important role in keeping cells attached. These molecules are proteins located on cell surfaces that allow cells to bind to each other. Changes in these molecules affected how strongly cells remained connected. Stronger connections allowed more stable, multicellular structures. Weaker connections allowed more flexible arrangements where cells could move within a group. The internal environment of multicellular organisms became regulated through coordinated cell activity. Cells work together to maintain balanced chemical conditions inside the organism. This regulation involved controlling levels of nutrients, waste products, and internal fluids. Cells responsible for regulation coordinated with other cells through chemical signals. Genetic regulation became more complex as multicellular life developed. Different combinations of genes were activated in different cell types. This allowed a single set of genetic material to produce multiple types of cells. The same genetic code led to different outcomes depending on how it was used in different cells. This process allowed greater diversity of cell functions within the same organism. Over time, multicellular organisms occupied many different environments in the oceans. Some lived attached to surfaces, such as rocks or sediments. Others floated in water columns. Some moved actively through water, while others remained fixed in one location. Each environment influenced how multicellular structures developed and functioned. Cell communication systems became more refined. Cells used chemical signals that could spread through small distances in water or pass directly between connected cells. These signals allowed coordination of growth, movement, and reproduction. Cells responded to signals by changing their activity levels or gene expression patterns. The stability of multicellular life depended on the ability of cells to remain coordinated over time. When coordination was maintained, Organisms could grow and survive under varying environmental conditions. When coordination is disrupted, multicellular structures could break down into small groups or individual cells. The persistence of coordination supported long-term existence of multicellular forms. The emergence of multicellular life marked a major stage in the history of living systems on Earth. It involved gradual changes in cell behavior, structure, communication, and genetic regulation. These changes occurred over long periods through continuous small variations in biological processes. As multicellular life continued to develop, the internal organization of organisms became more defined through steady changes in how cells behaved and interacted. Cells that remained together for long periods began to form more stable arrangements that did not easily separate during normal growth and reproduction. These stable arrangements allowed groups of cells to function as a single unit, where each part contributed to the overall activity of the organism. The relationship between cells became more dependent on chemical signals, physical attachment, and shared use of nutrients and energy. One important change involved the strengthening of cell-to-cell attachment systems. The outer surfaces of cells developed more complex structures that helped them remain connected. These structures included proteins and other biological materials that formed connections between neighboring cells. As these connections became stronger, multicellular organisms were able to maintain their structure even when exposed to changes in water movement, temperature, or chemical conditions. This stability allowed organisms to grow larger without falling apart into separate single cells. At the same time, internal communication between cells became more organized. Cells began to release chemical substances that carried information to nearby cells. These substances could influence how other cells behaved, including whether they divided, moved, or changed their internal activity. Some cells became more sensitive to certain signals, allowing them to respond differently depending on their position and role within the organism. This sensitivity created differences in behavior, even among cells that shared the same genetic material. As these communication systems developed further, early forms of regulatory control began to appear. Regulation control refers to the way cells manage and coordinate activities across the organism. Certain cells began to act as centers for receiving and sending signals, helping to coordinate the activity of other cells. This coordination ensured that growth occurred in a balanced way, and that different parts of the organism developed in a controlled manner. Changes in gene activity played a central role in shaping multicellular organization. Genes within cells did not all remain active at the same time. Instead, certain genes were activated or deactivated, depending on the needs of the cell and its position within the organism. This selective gene activity allowed cells to take on different roles even though they shared the same basic genetic material. Some cells became more focused on structural support, while others specialized in processing nutrients or responding to environmental changes. Over time, this process led to the formation of more distinct cell types. Each type of cell carried out specific tasks that supported the survival of the organism. Structural cells provided stability and shape. Nutrient processing cells absorbed and distributed energy-rich compounds. Protective cells formed outer layers that reduced damage from environmental conditions.